So, thank you. This is the Georgia Tech PI session. We'll start off, he's getting ready, with Professor Simon Sponberg, who's an assistant professor in the physics department at Georgia Tech. He's been with us now less than a year. The lab is already up and running and producing very cool results, some of which I'll tell you about today. The second talk will be a shorter talk, originally scheduled to be given by my colleague, Dr. Flavio Fenton. He couldn't make it, so his postdoc, Ilya Uzlek, will give the talk. All right. So Simon's ready. Take it away.
Okay, great. Is this on? Can you guys hear me okay back there? Great. Okay, so my name is Simon Sponberg, and as Dan said, I just started at Georgia Tech this past year, and I actually have a minority appointment also in the School of Applied Physiology, and that's what I'm going to talk to you today about. Is one of the things that we're doing at the iPoLS at Georgia Tech is looking at this physiological band organization, looking at how physics and physiology can interact, and I'm specifically going to talk to you about that today in the context of locomotion in animals. So a little bit different from the earlier talks today. But what gets me excited in the morning is looking at how animals navigate through their environment. And animals are particularly impressive because I think they've evolved to negotiate pretty much every environment on this planet. And they've been able to do so using a diversity of forms and morphologies, but generally all animals have to face the challenge where they have to acquire, process, and act on information in their environment. And so we usually think of that as the domain of neuroscience, how the brain acquires and processes information. But in order to do that, the animal has to interface with its environment, and then therefore it's subject to the physics that governs its sensors and its actuators, as well as the environment around it. And so we have a hawk moth here. This is Manduca sexto, which I'll be talking about mostly today. This guy can hover in midair. This is slowed down about 30-fold. That's a dynamically unstable behavior. If it doesn't do anything, it'll go pitch unstable within a couple of wing beats, and if it doesn't do that, it'll go laterally unstable through a couple of roll motion. And so it has to be continuously acquiring information from its environment and updating its dynamics just to stay in midair. But even more impressively, it can feed from flowers that are moving in the wind. It can cast back and forth, and it can do all of this in very low light environments. But we have other animals that are really good at getting across their environment too. So this is the cockroach, Blubberus discredalis. So this guy can run over very rough terrain. And one of the interesting things that it does is it uses its antennae as tactile probes. And what we've been able to show is that you can actually make a very basic dynamics model. So we actually do that modeling of running cows, except in this case it's running cockroaches. And it turns out you can discover that the information that's processed just in the primary sensors in the antennae is already preconditioned to act as a stabilizing control input for the dynamics of the body. So the way that sensors are acquiring information and processing it, even at the very first level scale, is already tuned to what the animal needs in order to stabilize its dynamics. And we also look at other mechanisms that aren't necessarily neural. So this is a gecko climbing up a vertical wall. I like to show this image because it's very difficult to tell if the gecko is climbing vertically or running horizontally. And the interesting thing with the gecko is it's attaching and detaching its foot pads in as little as 40 milliseconds. So those foot pads, as many of you know, adhere by the van der Waals forces. And so the gecko is facing a locomotor challenge here that is relying on some of the weakest molecular forces in the animal. And it's really dependent on then getting its feet close to the surface, right? Again, it cares about geometry rather than chemistry. The van der Waals forces adhere through almost any two surfaces as long as they're polarizable. And so the gecko really needs to be able to get close, so it has these very fine foot hairs that are down to the order of 300 nanometers. And it can make very close contact with the surface. And the trick for the gecko at the locomotion level is being able to pick up and detach its feet and reattach them in as little as 40 milliseconds. So I thought I'd give just a little bit of an introduction to the kind of field that I work in, because a lot of you may not be fully familiar with it, particularly the students in the audience. So I'm studying what's called neuromechanics, which is the intersection of the neural and mechanical systems in the context of the physics of locomotion. And so very basically, we have the nervous system. You can think of the nervous system sending motor commands, this is electrical activity, to muscles. And muscles themselves are electrically active too. They have action potentials. And they actually transform those action potentials into mechanical work and power output, which produces forces and torques on the body, which through its interaction with the environment creates movement. And of course, we have feedback information. information that's coming in there. Animals are blind in their environment, so we have sensory information about the state of the animal in the environment, but also the internal state of the animal. There's sensors in our muscles that tell us about the stretch and the forces that those muscles are producing. And those sensors would have characteristic delays that are actually quite long. For many animals, it's on the order of between 50 and 100 milliseconds. So the time delays in these systems can be quite significant. But there's an error that's missing here, too. There's also a mechanical feedback error here. And what we mean by that is that there's state dependence on the forces and torques that the muscles actually produce. And this is one of the features that's been less considered a lot in the role of stabilizing locomotion, particularly from a neural perspective. So if I just take a muscle and I activate it at a constant level and I stretch it out different lengths, as a classic muscle physiology experiment, you'll get a force length curve out of it that looks something like this. And this is a combination of nonlinear passive elasticity and also an active response based on the matrix of contractile proteins that underlies muscle function. So you actually have a living crystal here inside the muscles that produces these forces. And so muscle has this feature then, of course, where if you stretch it out, I don't need to send or change my neural activation to that muscle at all. It will automatically start producing more force. And if that allows the muscle to shorten, you can have a restoring force just based off where the muscle is operating on its force length curve. So muscles themselves can contribute advantageous properties for stability and maneuverability independent of the nervous system. The dynamics of how animals run can also be really important. So this is an earlier experiment that I did with running cockroaches over rough terrain. So this is a Gaussian distribution of surface heights, and as the cockroach runs over, you can record the electrical activity of the brain descending to the main muscles that are involved in having the animal elevate itself over obstacles. And the interesting thing that you see is that in this experiment, when the cockroach is running over these rough terrains, is the brain is not modulating the activity of these muscles. The brain is sending sort of a constant, continuous feed-forward set of commands to these muscles. And it turns out that if you look at the underlying physics, if you do that model of how the cow runs or how the cockroach runs, it doesn't really matter. They use the same underlying nonlinear stiffness that we use when we run. And those models have can be passively dynamically stable, even without damping, which is very interesting. So you can get asymptotic stability without damping, which is very interesting. But that's for another talk. You can do the same thing. You can instantiate those underlying physics into a robot. You can have that robot then use the same parameters, scale up as the cockroach running over a scaled up version of the same rough terrain, and you can show that the underlying physical model is sufficient to negotiate these surfaces. So this is what we do. We look at the interaction of motor commands, muscles, and movement in the generation of locomotion. We have to remember that all of this sort of comes from three different fields that have their roots in biology, neuroscience, biomechanics, and muscle physiology. And all of this operates within the context of the environment. And what I'm going to particularly talk about today is how we have used concepts from physics in a way of looking, not just using a tool from physics, but looking at this system as a dynamical system, as a set of molecular motors that are operating in a statistical mechanics sense to generate muscle force output, looking at information flow through the environment. All of these different approaches we can use to treat these systems as physical systems, and then hopefully discover some new physics out of it as well. And so what I particularly do in my lab is I try to not just look at one of these boxes in particular, but what I'm really interested in is making some predictions from one box to another. So if we know something about how the animal runs, can we ask the question instead of what does the nervous system do? Can we ask the question of what must the nervous system do? Meaning what must the nervous system do in terms of the dynamics in order to stabilize the body dynamics of the animal during locomotion? Or if we know something about how the nervous system sends out commands, what does that tell us about the muscle physiology and how it might translate those demands into favorable forces and torques for the end? So that's what we're going to talk about today in a few specific examples. And I'm going to focus on this guy called complementary sensor. And this is about hovering fly overhead. And what I'm particularly going to do is I'm going to lay out a little bit of a framework first. And so the idea is if you take a look at those systems that I had written before, this is an inherently feedback system. And this is one of the very important characteristics of free behavior. Free behavior is a feedback system. So if an animal is tracking a reference, like a moth is tracking a flower, what the moth's nervous system sees is not the flower. Right? What the moth's nervous system sees is the difference between the flower's movement and its own self-generated movement. And this is something that we forget sometimes when we take the animal out of the free behavior context and reduce it down and put it into a tether preparation. We're actually changing fundamentally what the nervous system is perceiving about the world. Okay? But that can be an advantage. So one of the features that we need to remember is that free behavior is inherently closed loop. It's also typically multimodal. Animals typically have multiple sensory modalities, different types of sensing, olfaction, vision, and chemoreception that they can use. So there's usually a multiple input, multiple output consideration here. And not just can you provide references or signals that drive this system, you can also look inside the system and you can not just record motor commands or record the forces, but you can provide disturbances here, or even systematically rewrite these by tapping into the nervous system and manipulating the signals that the brain is sending to the body. So what we can do then is we can do a series of experiments where what we do is we can open loops. And so by removing a specific loop through sensory ablation or degradation, or I'll show you some more subtle ways to do that in the experiment today, we can actually change the system dynamics. But we're not just sort of arbitrarily changing the system dynamics. What we can actually do is create quantitative predictions about how those shifts in topology from the closed loop system to the open loop system, or partially open loop system, should affect the system dynamics, given our understanding of these different boxes. And we can do the same thing in the other direction. This is actually my favorite way of doing it. We have remarkable access to physiological systems now. You guys have heard about the genetics of all the multi-electrode rays. We can record from hundreds to even thousands of neurons simultaneously now in the brains of animals, particularly in reduced preparations, but also in free behavior sometimes. And so if we take the nervous system out of the animal and we stimulate it, now again, the nervous system is just receiving that reference signal, not the error term. It doesn't have any self-motion being that good. This is the classic experiment of like taking a brain and putting it into a dish. And we can record the output, and that experiment can be very useful, especially when we put it into the context of the other kinds of topologies of the system. We can actually do the same thing for musculoskeletal prep. We can activate it, stretch it back and forth, do typical material testing on the muscle, and look at the forces that it produces, and treat it as an input-output dynamical system. And we can do that for the integrated animal, too, if we tether it. So now if we take them off, for example, and stick it on a stick, and give it a visual input. Now we have it in an open loop situation. Whatever the ball tries to do is rigidly tethered, so it can't change the visual input that it's receiving, so it's in an open loop context. And so what we can do then is we can close those loops by putting them into virtual reality arenas or relating them directly to free behavior experiments. So by coupling, you heard a little bit about this with the mouse running around yesterday, if you actually now record what the animal's motor output is, or you simulate the body dynamics and calculate what those motor outputs would be, measuring the torque on a tethered animal or measuring that trackball that the mouse runs on, you can update the visual system. And the nice thing about doing this is when you have it in a virtual reality arena, now you can change this feedback, you can change the rules on the animal. And so what you can do is by going through these different kinds of experimental preparations, which typically are done in isolation, if you actually have an eye for how that's changing the dynamics of the situation, you can take experiments in one case and make predictions about how they should affect the dynamics in another case, and test the ideas of what the component systems are. And that's what I'm going to give you a specific talk about today. So if that seemed a little abstract, let me make it a little bit more concrete and come back to it. Okay? So the system that I'm going to focus on today is how animals see incredibly low light environments. And I think light is one of the most interesting biophysical quantities because it varies more than almost any other quantity an animal typically has to deal with. From midday to midnight, sort of the brightest to the darkest levels, an animal will go from about 10 to the 4th candela per meter squared to 10 to the minus 6, so 10 billion fold, which is quite variable. And we actually have very good visual systems. We can, maybe you've heard that our visual systems may be able to detect a single photon. We don't actually respond behaviorally to that. But more importantly, our visual system, we only have a small range of color vision. If you've ever tried to go and pick up a shirt in the morning without disturbing your partner in bed, and if you pick up the shirt, you'll notice it, and in dim light, you'll notice that you can't see the color of the shirt. And that's because the color receptors in your eyes actually fail right about 10 to the first candela per meter squared. So we have black and white vision that goes down to lower levels, but we typically maintain most of our activity during the day. We're fairly diurnal animals. hawk moths, these large 3-gram moths that look like hummingbirds, actually have color vision that extends all the way down to sort of an overcast scarlet gray. So they're able to maintain their color vision quite a bit lower, and they maintain their activity during that time too. And so one of the interesting things here is that these crepuscular animals, animals that are active during dusk or dawn and not just strictly nocturnal or diurnal, actually may face a greater challenge than just truly nocturnal animals because they actually have to deal with this large range of light. They actually have to be able to adjust. And that's what I want to focus on today, is how do these animals adjust their neural systems and their mechanics in order to maintain behavior at different light levels. So this is the head of the moth. You'll notice the first features that should jump out at you are these large compound eyes. The brain is right behind where these eyes are. This is the proboscis curl here that we'll look at in a minute. And inside the brain of the animal, a lot of the brain's nervous system is dedicated to vision. And so there's adaptations in each of these levels for adjusting for low light and sensitivity. So the first level is just sort of some optical adaptations. Instead of the typical inset compound eye where you sort of have one lens for one photoreceptor, each of these lens photoreceptor combinations is called a monotidium. In moths, you have superposition eyes, where as light levels drop, there's a pseudo-pupil that retracts going through this gap here. And then there's proteins that actually move in the ommatidia that have different refractive indexes. And they can refract light now from multiple ommatidial lenses into individual photoreceptors. So you have something that acts sort of like an aperture on a camera, but has a different physical mechanism. So as light levels drop, you can think of this as a Gaussian filter in space that is expanding its width, and so you're getting larger spatial integration, and you're sacrificing some resolution. There's another level of spatial adaptation where at the next level of the nervous system, they have neurons that tap into multiple photoreceptors. So these neurons will tap into one photoreceptor over here, one photoreceptor over here, collect light, and again, it will cool it with a second level of sort of spatial integration. And these are great. These adaptations help a lot. They actually give the moth about 1,000-fold increased sensitivity, which is great. But that's not 10 million-fold, which is what the moth needs in order to be able to adjust to the different light levels. So there's been ideas that there has to be some other mechanism for it. And what I want to focus on is how motion is detected in these animals. So when in the visual system, if you have just 3 photoreceptors, you can imagine an object going from left to right here. Those, what's going to happen is as it passes through the first photoreceptor, that's going to send a signal around. Inside the brain, it also has a lateral branch to that signal where it's split off, and it's passed through a low-pass filter, which you can end up modeling just as a simple time delay. And so if that time delay is too bright, then as the object goes from left to the right, once the object passes through this second photoreceptor, you'll have a coincidence or a correlation between the delayed signal from the first photoreceptor and the incoming signal from the second photoreceptor, and you'll get a very large response. So interestingly, when neuroscientists now in the open loop, right, they've taken this out and they've looked at how this visual circuit responds, and what they've done is they've mapped contrast sensitivity. This is the minimum amount of light-dark contrast, so how black and white you need to give a stimulus to the animal's visual system in order for it to detect motion. And it's an odd stimulus, but it works well for visual neuroscience. And you just look over the temporal frequency. So here you have light and dark bars that are moving back and forth. And as you change those temporal frequencies, you can see that the moth is able to maintain its contrast sensitivity from dusk all the way down to the moonlight levels. And in order to do that, what the neuroscientists had proposed was that perhaps there is an increase in the time delay in this filter. Okay, so there could be a neural strategy where you now have temporal integration in addition to spatial integration. You slow down your visual system in order to integrate information for a long time and get increased light sensitivity. So this was the prediction from this open loop prep. And we wanted to go in and test this, but it's actually very hard to go in and dissect apart this circuit inside the brain because the cells that are involved are very, very small. And so what we wanted to do is when we looked at this, we said, well, what are the consequences then that would predict for the dynamics of a freely flying animal? And so what we'll do is we'll just make it a general qualitative prediction first, and then we'll make it more quantitative in a minute. We'll say, well, if luminance levels are dropping, we have an increase in the effective time constant, then that would suggest that the animal is going to lag behind moving objects more as light levels drop. I'm just going to have the analogy is as you slow down the shutter speed on a camera, so you're taking longer exposures. If you take a series of images, they're going to start blurring together. You'll be less able to detect high speed motion or high frequency motion. So to test this, what we do is we make a bunch of 3D printed flowers, and then we mount those flowers onto a robotic apparatus, and now we can wiggle flowers back and forth in any arbitrary way that we want, and we'll use a very particular stimulus. Here's a moth that we let land on the flower just for scale. Normally the moth's feet while hovering in midair, and you can see here, this is a very long proboscis that they uncurl from their mouth. And they'll actually probe the flower until they get the proboscis into nectary, and then they'll track that nectary back and forth with the proboscis in it. So what we're going to do is we're going to do a frequency response analysis on the moth's dynamics. We're going to take the sensory input is going to be the flower's movement, the motor output is just going to be the moth's kinematics in this case. And what we can do is we can look at the response gain, the ratio of the amplitudes and of the moth with respect to the flower. So if the flower moves 7 centimeters to the right and the moth moves 7 centimeters to the right, that's a gain of 1. And we can also look at the phase response of the system. And of course, you can do this in a complex domain using the ratio of Fourier transformations. And so that means we don't have to look at any individual frequency. We could, of course, step through and do multiple experiments. But we can combine multiple sinusoids in one experiment and gather multiple points at once, or even very many points at once. And by interpolating through that, we can get the gain in the phase as a function of frequency. And in engineering, this is usually called the Bode plot. And so what this is going to do now is it's going to characterize the closed loop dynamics of the freely flying system. And we're going to try and relate what would happen in these closed loop dynamics if you insert delay in the system. Okay, so this is what happens when the moth is trapped in that flower. And you can see it's casting back and forth. This is actually slowed down about 4-fold so that you can see it more easily. The moth is very good at tracking motion. It can actually, if we take a look at the flower's position over time, what you can see is that what we've done is we've driven it with 20 different frequencies. These are all prime multiples of each other so that the harmonics don't overlap. They have a particularly decaying relationship here. That's because what we've done is we've tried to match up their peak velocities rather than their peak displacements. That prevents the biological system from saturating and allows us to characterize it. We failed a little bit up here just because of our motor. We get a little extra high frequency, but it turns out the moths can't track these couple of our very highest frequencies. So that doesn't matter too much here. And then here's the moth's response. And what we can see is the moth is, if we just take Fourier transformation of the moth's response, we see the moth is responding at each of these characteristic frequencies. And it actually has a response all the way up to about 10 hertz. And we can measure the coherence here, which is the cross-power spectral density normalized to the spectral densities of each of the responses. And this is a measure, it's sort of, if you're familiar, it's sort of like the frequency domain is equivalent to the correlation coefficient. It gives you a measure of how well a linear model could approximate the response to the system at the given driving frequencies. And you can see that our coherence is relatively high, even out at relatively high frequencies. This is not, however, a great test of linearity, because, of course, nonlinear systems can create high coherence as well. So we've actually gone in and explicitly tested linearity through scaling and superposition testing. I can talk to people about that, but it's sort of a detail I'll gloss over for now. It turns out the system is highly linear in free behavior over the range of frequencies that we're looking at. Okay, so what we can do then is we can look at the gain and the phase response of the moth. And so what we first see is let's do it at high luminance, the equivalent to early dusk. And what we can see is that the moth is going to respond sort of like a bandpass filter. It starts out with a gain a little bit below 1, and then between the frequencies of about 1 and 2.5 hertz, it's tracking with a gain of 1 before falling off. And the phase is going to just decay here. And I've put the frequency on a linear plot here rather than a log plot. And you'll see why I've done that in just a minute. But before I get into that, we can just say, so as light levels drop, our prediction was that the phase lag should increase. Right? The moth should lag further behind the flower in low light conditions at the time the light goes up. And in fact, that's what we see when the animal tracks under low luminance. But we see some other interesting features that we didn't predict. For example, we have this overshoot, where the moth now, in low light condition, at these intermediate frequencies, will actually go further than the flower. If the flower moves 7 centimeters, the moth will go 10 centimeters. So what we could do is we could say, well, let's just estimate a time constant for this system, which is just a constant linear regression in in the linear domain here, which is why we have this on a linear axis. But this is a very sort of gross approximation of what the overall response characteristics of the system is. If we go ahead and do that, though, we can fit a single time constant to those two responses and say, oh, the moth is going from about a 60, effectively a 60 millisecond time constant to an 80 millisecond time constant. But that's not really what we were predicting about the system, right? What we were predicting about the system was that there was a delay inside the nervous system, not that there was a delay on the overall system dynamics. And that's a very different prediction. So what we had here is under the high luminance condition, we had characterized the input-output relationship of the visual motion to the body kinematics. And what we had really, our hypothesis was really that there should be a delay inside this nervous system, which is actually detecting the error in the visual information, the difference between where the moth, how the flower is moving and how the moth is moving. And so the low luminance response shouldn't just be a delayed version of the high luminance response. It should be the high luminance response with the delay inside the system. Now, what we can do is we can go ahead and put the delay inside that loop, but the relationship looks a little different. So here's the high luminance response with respect to the Laplace variable, just with respect to frequency for I omega here. So you can think of this as how the gain in the phase response at each of the different frequencies. And so what we can do is we can open that loop, and that has a specific relationship now, where the open loop response should be related to the closed loop response over 1 minus the closed loop response. And now what we can do is we can add our delay in that system. So now the delayed closed open loop response should be equal to just this, the delay in the frequency domain, this exponential term. And then what we can do is we can reclose the loop, and we can create a prediction for what our low luminance response should be. And that relationship is here. So now what we have is it's a more complex relationship, but it still just has two simple dependencies. The low luminance response should just depend on how the moth responds at high luminance. And it should just depend on this error term, which has one free parameter, which is tau here, the time delay in the system. Okay. So what we can do then is we can take our high luminance response in orange, and we can predict our low luminance response, and we can see how well our prediction lines up with the actual response here. And when we do that, we find that we have a very good agreement between the low luminance response and our prediction. And in fact, we're even able to reconstruct this unexpected overshooting in the visual system at the higher gain. So by going in and applying our delay inside the closed loop model and creating our dynamics prediction about how the system should be responding in the closed loop, we're actually able to get very good agreement here. So what we've shown is that the moth does slow its brain down in order to track flowers in low light. But there's a question then that we want to bring that back to the biology and say, what does that matter for the biological system? We do both physics and biology, right? So, well, for the animal, gain and phase are sort of difficult performance metrics to look at because they're two different metrics and we don't know which one is necessarily important. So let's recombine these into one metric of performance for the animal. So if you remember, we just have gain and phase because we thought about a complex plane with gain as your radial coordinate and phase as your polar coordinate. And so then that means anything on the unit circle is going to be having a gain of 1, so the moth is going to be moving with the same magnitude as the flower, but with potentially different delays. And perfect tracking is the 0.10, right? Full gain with 0 time delay, 0 phase lag. And so what we can do is we can simply take the distance in the complex plane from where the moth is actually tracking to the 0.10 and use that as an error metric. And so, for example, if the moth is tracking with a gain of 0.5 and a phase lag of pi over 4, then we get an error of 0.7. And if the moth is tracking it with a gain of 1, but a phase lag of pi over 2, then we get an error of 1.4. And actually, if we go all the way over here, where it's fully out of phase with the flower, and the moth is all the way to the left and the flower is all the way to the right, we get an error of 2. So what we can do now is we can plot the tracking error for high and low luminance across different frequency ranges. And what you can see is that there's sort of 3 bands here. From sort of low frequencies to about 1.7 hertz. The moth is doing particularly well in both frequencies. The error is overall low, and there's no difference between the high and the low conditions, luminance conditions. In the intermediate frequencies, the moth is doing much worse in both conditions, and it does even worse in the low luminance condition. And at the highest frequencies, the moth it goes back towards 1. And one of the important things to look at here is the tracking error of 1 is what you would get if the moth was at the origin, which would mean that it just wasn't moving at all. Right? And so the moth at these intermediate frequencies is actually doing worse than if it didn't try to track the flower at all. So the dynamics that it's using are somehow creating worse performance than if it just didn't respond at all at these intermediate frequencies. Which led us to wonder, what are the frequencies that matter for moth movement? So we did what I sort of think of as the least glamorous field research you could imagine. We went to the botanical gardens, this was at the University of Washington campus, and we grabbed 5 different hawk moth pollinated flowers from the greenhouse. And we put them outside and we let them blow in the wind. And so we just used natural wind from about 0.1 to about 3 meters per second. And so if you've never seen a high-speed video of a flower blowing in the breeze, this is a petunia blowing back and forth. You can watch that for a while. We can track that flower moving back and forth. And what we can do then is we can decompose it into its constituent frequencies and look at how well that matches up with the frequencies of the moth's response. So what I'm going to do is I'm going to add a second plot here now below where we can look at the frequencies of the flowers. So what do you get, and here's the riddle for the day, what do you get if you take the Fourier transformation of a flower and square it? You get a response that is flower power, right? Or flower power. And so we can plot the flower power versus the frequencies that the moth tracks at. And we can do that for petunia, and what you see is that right at about that 1.7 hertz frequency regime, the petunia sort of stops moving. There's no frequency components at that higher range, and that's actually true for the other 4 species of flower as well. So the story here is that 95% of the flower power is below the frequency regime at which the moth sort of stops tracking well, and more importantly, where it incurs a cost for tracking low luminance. So the story here is the moth has slowed down its visual system in order to increase its sensitivity to low light, but it's only done it to the point where it avoids any potential performance trade-off in its ability to track flowers based off of the frequencies that the natural flowers move at. Okay, so it's finely tuned to the dynamics of the flower that it's interacting. The last thing I want to talk about is I want to take this back out and say, remember, most behaviors are multimodal. Animals usually have multiple sensory modalities that they can use. And I want to talk to you a bit about some results that are making me rethink a little bit how biological locomotion works. And so this project started off with saying, well, remember that when the moth is flying, it can see that flower, but it's also got this long proboscis that's stuck all the way down into the flower. You can actually see it wiggling around in the nectary down here. Right? And we know that the proboscis isn't stiff enough to provide any force on the moth. The flower isn't pulling the moth around like it's on a leash. In fact, the proboscis is usually not in contact with the side of the flower. But the proboscis could be a sensory structure. Whenever you have a biological structure and you ask, could this structure be a sensory structure? The answer is yes. There are thousands of millions of sensors in every biological creature. And in fact, if you look at the proboscis here, this is a curl up like a party favor inside the moth's mouth. If you extend it out and you look at the tip of it, you'll see that there's these little structures that look like domes and these little structures that look like hairs. We don't know what those structures do specifically, but they look a lot like mechanoreceptors in other biological systems. So we could go in and we could try and record from those sensors, and we could characterize the responses, and we could do all the nice neurophysiological techniques that we would normally go about doing. And in fact, we're starting to look at doing that. It's actually really hard to record from this long proboscis-like structure. But what we can ask in general is that, are there characteristics of the system dynamics that tell us if the moth is using mechanosensory information from the proboscis in addition to vision? And so what we can do is we can set up a new experiment where we take that robotic flower and then we decouple the face of the flower and the nectary of the flower, and we put them on independent motors, and we can wiggle them back and forth separately. So in one case, we're going to have the face of the flower stationary, and we're going to have the nectary wiggling back and forth, providing the mechanosensory stimulus. And in the other case, we're going to have the nectary stationary, and we're going to wiggle the face of the flower back and forth, which will provide a visual stimulus. And that looks like this. So here's these videos getting up. We paint the nectary black. I put a little white dot on there so you can see it. So the moth can't see the nectary. There's also a very, very thin slit here that the proboscis can move through. And you can see that when the nectary is moving, the moth is going to track the nectary back and forth. And when the face of the flower is moving, but the nectary is stiff, or stationary, the moth is still tracking the visual motion as well. So the moth is tracking both the visual and the mechanical stimuli independently here. This little thing here that you see out is just a little tuft of cotton that has the artificial scent on it that we use to stimulate the moth's appetitive response. It's active. All right, so what we can do then is we can characterize the responses to a visual and a mechanical response alone. And what we see is that we get lower responses overall than in the mechanical, where we have both the mechanical and the visual system moving together, where we have the intact flower. That's the M plus V up here. So that's the original experiment here. We just have the nectary moving, the mechanical reference, or the face of the flower moving, which is the visual reference. So we can get these responses, but what do they mean? What can we extract from these? It's a little hard. We can just say qualitatively, well, there's some differences here. There's some interesting things going on here. One thing that you'll notice is that the visual system has a phase lead on it, and the mechanical system has a phase lag on it. That actually makes good sense. Visual systems tend to detect velocity, so you would expect a 90-degree phase lead on the system if you're detecting the velocity of that. Of course, it's not quite 90 degrees because both it and the mechanical system are going to have inherent sensory delays to them. So they're going to have a set delay, in this case from 0 or from 90. So that actually makes much better sense than what we were originally looking at, which is a phase lag exactly pegged at 0, which was interesting in both of these. Okay, so, but what can we do to assess whether the visual and the mechanical system, how are they contributing to motion? Well, the first thing that we can notice is we have an ablated vision or ablated mechanoreception. They're both present in both of these cases. All we've done is we've decoupled the reference signals, and then we've removed one or the other. So in this case where we move the back of the flower and hold the front of the flower stationary, we've set the visual reference to 0. It's not moving. But as soon as the moth moves, we're going to get a visual error, right? Because the moth is going to move relative to the vision. So we have to take into account that we still have both mechanical and visual dynamics going on in any of these behaviors, even where we've decoupled the face of the flower and the back of the flower. So we have to be very careful how we combine these systems if we want to ask questions about whether mechanics or vision are, for example, more important, or how they combine. Okay, same thing happens when we look at the visual reference and we keep the mechanosensory reference 0, then we're setting this one to 0, but there still could be a mechanical error term when the moth starts to move. Okay. So what we can do is we can look at the mechanical and visual responses, and what we're going to do is we're going to say, let's consider the input and the output here for the flower's motion, the kinematics, R to Y. And we're going to model this sort of as simply as we can imagine. Let's say that we just have some dynamics of this vision response here, V of S, some mechanical response, MS, some body dynamics, BS, and hopefully not the whole talk is BS. And we can make some simple predictions about how are those combined. So let's think, for example, let's just posit the simple hypothesis that the moth is linearly combining the mechanical and the visual inputs. How would we test that? Well, we can look at the responses and we can say, well, in the numerator here, we have the open loop response, which is V times V in the vision case, or M times V in the mechanical case, or V plus M times V in the combined normal response to the flower. But in the denominator, the closed loop response, the response to self-motion is the same in all cases, because you both have the mechanical and the visual response. So you have the denominator the same in all of these cases. So we can combine those now, and what we can say is that if we have the visual reference only and the mechanical reference only, does that produce the combined mechanical and visual reference? If we go back to these terms, we can add the response here and add the response here. We should get the combined response if this hypothesis about a linear controller is accurate. So what we can do is we have to do that combination again in the complex plane. We can't just add gains and add phases. So if, for example, if this was our response to the mechanical stimulus alone, and this was our response to the visual stimulus alone, and then our combined response would be here, and we can compare that to the actual response. And when we do that, we find something that, to me, was pretty surprising, that the visual system, that the predicted response of the mechanical and the visual system actually matches up very well with the actual response. There's a little bit of disagreement here. Actually, this has gone away now that we've collected some additional data. So even at these higher frequencies, these line up. I just haven't updated the slide here. But more importantly, in this regime where you have 95% of flower power, again, you have very good reconstruction of what the combined response is from just knowing how the moth responds to the mechanical and the visual stimuli separately. And this was surprising to me because the rule in neuroscience is generally that you have reweighting and nonlinearity. But for this behavior, the moth wants to respond to the flower nicely linearly, right? It doesn't want some sensitive dependence or any kind of nonlinear response to a flower's motion. If the flower moves 1 unit to the right, it wants to move 1 unit to the right so it maintains good tracking. So what it's trying to do here is we set up the task, and this is true for most tracking tasks, most postural control tasks, is that the goal of the system actually should be to generate linear dynamics. But if that's the case, then we should be able to reconstruct, we should be able to deconstruct any kind of response that the moth has into its visual and mechanical components and actually drive the moth in any way we want. So let's set up a crazy experiment. Let's take the visual motion of the flower and let's move it in 5 different frequencies. Okay, so this is the full stimulus we're going to give to just the face of the flower. And at the same time, we're going to move the nectary of the flower in this way with the same 5 frequencies, but with a different amount. And I've constructed these stimuli in a very particular way. I've sort of back-calculated from the transfer function, from the dynamics of the combined system, what the response should be at each of these frequencies. And I can predict that the moth, with respect to just the mechanical system, should respond like this. And with just the visual system, should respond like this. So I've set up these stimuli to produce the exact same response in the moth to the visual and the mechanical stimuli. But I put them out of phase with each other. So now what's happening is the front of the flower should be moving in a very complicated manner, and the back of the flower should be moving in a very complicated manner, and they should exactly cancel out with respect to the moth. Or actually, I've canceled out 4 of the frequencies, and at 1 of the frequencies, I've made the stimulus constructive. So what we really predict here is that we have these complicated movements, and now the moth should move like a nice sinusoid at 0.7 hertz. And in fact, when we do that, here's the response of the moth to those frequencies, and so we can actually get the moth to track at exactly 0.7 hertz by deconstructing the stimulus and then creating a destructive stimulus at all the other frequencies. And this is actually more interesting to look at in the complex domain. We reconstruct about 90% of the moth there. So in the complex domain, here's the 5 frequencies I was giving to the moth. Here's where we were predicting the mechanical response should be. Here's where we were predicting the visual response should be. So if those systems add linearly, the moth should respond at the origin here, 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 and here, and it should produce a gain of 2 in this case. And here's the responses of each of the individual moths. So you can see that we're getting very good reconstruction, a very good predictability of how the moth should be able to respond. So I can give it now an arbitrary visual stimulus, arbitrary mechanical stimulus, and target the moth's motion in any way that I want. And in fact, we can say, well, maybe there's something special about 0.7 hertz. Let's do the same thing, but now let's make 1.9 hertz constructive. And when we do that, we see that the moth responds very well right at 1.9 hertz as well. We get a little bit of bleed over into 1.3 hertz, and we're exploring why that is right now. But only at 1.9 hertz do we get anything that's outside the unit circle. So what this means is that the moth is responding with a very simple linear summation of its visual and its mechanical stimuli. And this is odd because, and the overall response is itself linear as well. This is a little odd because we know that the underlying physics of flapping flight at that level is fairly inherently nonlinear. It's very difficult to capture with linearized models. We know that the visual system is responding nonlinearly. That motion correlation diagram that I had earlier has a correlation to it. We suspect that the mechanical system is as well. And so what we have here is we have a system, the moth, that it has nonlinear constituent physiological systems that it's putting together to create nice linear dynamics. Now, of course, any nonlinear system, if you look at it at a close enough scale, can be looked at and have linear-like behavior. Right? But over the entire regime of behavior here, we're seeing that the moth is maintaining sort of a nice linear response to the mechanical and its visual stimuli. And what I think is really interesting here is that we're having emergently simple dynamics out of the interaction of complex physiological systems. And so somehow the brain and the body are working together such that the way that they combine is producing nice linear dynamics. And that's what we want to study is the sort of principles of how the nervous system, the mechanical system, and the interaction of the body and the environment combine to produce these dynamics. So I will just end up by saying, so what we found is that the multiple sensory cues are combined linearly to produce this behavior. And we can actually predict it. Oh, and the one last thing about that is the predictions that I was doing were based on the population response of the animal, but I was predicting individuals. So each individual, I could predict their dynamics based off of the average dynamics of the population of moths, even without scaling for mass. Mass varies a little bit. All right, so just to thank a few people, the beginnings of this work were done when I was a postdoc with Tom Daniel, also working with Itai Roth at the University of Washington. John Dyer helped with a lot of the, particularly the simulations of the visual system. He's an assistant professor at Northwest University, and two really good undergraduates who worked with me. Robert Hall is now in Morocco teaching science to high school students in the Peace Corps, and Mary's a PhD student at Harvard. So thank you to NSF particularly for funding this and several collaborators. Thanks.
We have time for a few questions.
Very interesting. Okay, here's two experiments you got to do. You have a local anesthetic in the nectar. You do dose dependence of that, and then you do the second experiment where after proboscis engagement, you start reducing the light dose dependent and see how it fits your model. Okay?
Yeah. So the anesthesia experiment is surprisingly difficult to do, in part because the proboscis is muscularized as well, and they rely on being able to maintain tension in that proboscis in order to keep it unrolled from the body. So if you numb it, the moth just sort of freaks out and stops doing anything. So this is actually, but we're trying some other ways. We have some ideas of how we might be able to manipulate that. It's exactly what we want to do. And yeah, the light level, we're really interested in the time dependence of the time variance of these dynamics. The other thing that's happening, right, is the moth is feeding from nectar. The moth can actually eat 75% of its body mass in nectar. So you have a very interesting thing, whereas it's sitting there and feeding, its mass is increasing. And so the dynamics of the mechanics of the system is changing.
You can come and work with it.
Yeah, if you want to come play with the moth.
Just a quick question, because is the visual cortex of the moth, is it more or less, you assume it's the same as like with the humans, so they have cells that respond to, motions at certain increments, and does that have anything to do with the time response of your system?
Yeah, so we don't assume that it's the same as the human system, but we definitely, there's been a lot of neuroscience done on the moths, on the insect visual responses. It's one of the best studied systems. It's been a basis for a lot of computational neuroscience as well. So we know a lot about what's happening there. And what I want to emphasize here is that while they had worked out a lot of how the circuit might behave, they had this prediction about this sort of temporal integration time delay hypothesis that would allow it to collect more light. We actually did, I didn't talk about it here, but we did a full simulation of all the stages of cortical processing of vision to show that nonlinear system actually produces a linear prediction phase lag, so that it behaves a lot like a time delay over the range of frequencies that we were looking at. But we're going back in and looking at the neuroscience. I've actually have a collaboration going with some people who do the neuroscience on these moths in Sweden.
I think, Megan, you want a quick question, a student question?
Yeah, it's short. I can just yell.
Yeah.
So the moth movement, have you looked into if it's coming from changes in the wings or changes in the body?
Oh, excellent question, yes. It's definitely coming in part from the wings, but it looks like the abdomen plays a role through it by an inertial reconfiguration as well. The question is how much it actually does during closed-loop responses. And it's a very interesting thing to look at there. But they definitely do stuff with both their wings and their abdomen. But it's mostly the wings.
So, thanks.